All right, so we just did an experiment, right? And we had this balloon. I'm going to amaze you guys with my artistic ability. Yeah, nice. And so we had our little water faucet up top here, right? We got something going on like this. And we got some water coming out. We had this stream of water that came down and it bent towards the balloon. We bent water, right? Who knew you could do that? And so what, you knew you could do that? You've seen this experiment before. So what was going on? The balloon had static electricity, right, from Ari's hair, which is why she got put on the board. Congratulations.
Thank you.
And so because of the static electricity, the balloon was negatively charged. All right? And so what happened was the water molecules, which are made up of 2 hydrogens and 1 oxygen, these water molecules were orienting themselves such that the hydrogen was pointing towards the balloon, and it was attracted towards the balloon because these hydrogen molecules were carrying a partial positive charge. Now we might not have expected that because these are not ionic compounds, and ionic compounds are held together by opposing charges, right? What kind of compound is water? It's not ionic, but
Covalent.
it's a covalent compound, right? And so we don't think of, did you say that, Christian? Okay. We don't think of ionic compounds. You guys need different voices so I can clearly tear you apart when I hear the noise from that area, right? Can someone speak a little higher? Oh, covalent! So, no, yeah, it's not going to happen. So we don't think of these as having charges, but as it turns out, we mentioned the topic right at the end of class 2 weeks ago. And the topic was electronegativity. You guys remember that term? Does that at least a little bit sound familiar? And so what electronegativity means, some elements are more electronegative than others. So even though they share their electrons, they're kind of stingy sharers, right? If they're more electronegative, then they're not. It's like the kid that it's like, I'm going to let you play with my toy for like 2 seconds and then I want it back, right? So that's the way some elements are, especially fluorine. If you look on page 138, there's a table of electronegativity. And I don't know if you guys remember, but I said electronegativity increases as you go up the periodic table and to the right on the periodic table. And so if you look at the numbers on there, just kind of think of the comma that they've put in there as a decimal point if you're trying to figure out which one's more electronegative than the other. What is the most electronegative element listed in that table?
Fluorine.
Fluorine. So fluorine is the most stingy of all the elements. Fluorine is the most electronegative. So if I happen to give you a compound that's got fluorine in it, you know fluorine is going to be stingy and have a stronger hold on the electrons when it's sharing those electrons with another compound. All right? And so as it turns out, that's exactly what happens in water. If I look at hydrogen and oxygen on my table, which one is the more electronegative? Hydrogen or oxygen?
Oxygen.
Oxygen is. And so oxygen is pulling stronger. It's unevenly sharing its electrons. And so if it's got a stronger hold on the electrons, then it's going to carry what kind of charge? A partial. If it's got the electron more?
No.
Because electrons are negative, it's got a negative, right? And so that's why we've written a negative here, and we've written a positive for the hydrogen. So with the way that we write partial, hydrogen has a partial positive charge. We use that's a lowercase Greek letter delta. So hydrogen has a partial positive charge, oxygen has a partial negative charge. And that's why the water bent, because the water molecules rotated so that the hydrogen molecules were attracted to the balloon. And it caused the stream of water to move towards the balloon. All right? So the result, when you've got some element that's more electronegative than the other, the result is water is a polar, what we call a polar covalent molecule. And that is a molecule that has an uneven distribution of electrons, resulting in slight charges. So if we were to draw the Lewis structure for water, we might draw it like this. Right? The way the electrons are shared, they're being shared unevenly because the hydrogen is less electronegative than the oxygen. So we might draw it like this. We might say the electrons are actually being pulled more towards the oxygen. All right, and then we might put a line down here signifying that the positive end is the end where the H is. So sometimes you'll see it drawn like that because there's a partial positive charge here on the hydrogen, and with the arrows pointing that way, there's a partial negative charge on the oxygen. Okay? And so what we call these bonds now, these are just the covalent bonds that we learned about before, but because it's not an equal sharing of the electrons, we call those polar covalent bonds. All right? That should make sense. A polar covalent molecule has within it polar covalent bonds. So covalent bonds where the electrons are not equally shared. Now, what if we had one of our homonuclear diatomics, right? Suppose we had chlorine. We've got a covalent bond there, but is that a polar covalent bond? Is there an unequal sharing of electrons going on between these two chlorine atoms? There's not. Why not?
Because they're the same atom.
They're the same atom, so the electronegativity is the same, right? The one's not stronger than the other. And so in the case of a compound like this, we would say this is a purely covalent molecule. All right, and a purely covalent molecule I'm just going to write this. This is a purely covalent bond. And in a purely covalent bond, electrons are shared equally. And so since they're shared equally, I'll give you a second to finish writing that down. Since they're shared equally, then we don't have what? We don't have what?
Slight changes.
Slight
That's
charge.
that's an R.
Charges.
We don't have slight charges, right? We don't have, they're pulling equally on the electrons, so we don't have these partial charges develop. And so what do you think the oil, based on the experiment that we did, what do you think the oil was? A purely covalent molecule or a polar covalent molecule?
Purely covalent.
It was purely covalent, right? There were no partial charges in it, which is why it didn't bend towards the balloon. Make sense? All right. Let's. What about? Is it possible to have? So this is an example of an element that has. It's two of the same thing, so it makes sense that it would be pulling the same on it, and that the molecule is purely covalent. But what about a molecule like this? What do you guys think that molecule is? Is it purely covalent or polar covalent? Any idea? How can I find out? So
Polar covalent.
So Christian's going to guess polar covalent, but he
Okay.
based that on the periodic table. We know that as you go up and to the right, that it becomes more electronegative. For elements like this, it's kind of hard to tell though, because of where they're located on the periodic table. That periodic table we have on page 138 would be better, because that actually gives you the electronegativity. So when you look at those two on that table, how does the electronegativity compare with sulfur and chlorine? Sulfur and carbon, sorry.
They're the same.
They're the same, right? So this is actually a purely covalent compound, even though it's got different elements in it. It's purely covalent because they have the same electronegativity, right? So just because you see different elements doesn't mean you're going to have a polar covalent compound. Okay? All right. I want to talk about molecules in three-dimensional space. Ooh, right? Sounds kind of exciting. 3D molecules, right? I bought some special red and green glasses that we're all going to wear. Not really. Have you guys seen those before? The special 3D glasses? Yeah, they never really worked that well. Whenever I was a kid, they put some. Do they still do that anymore? They did like 3D things on TV, and you'd go like at the convenience store. They had these special glasses. There was some John Wayne movie. And you could go and you could get these special glasses for the John Wayne movie, and it had the red, green, and you were going to be able to watch it in 3D. It was really lame. It didn't work at all. It was a terrible experience. Maybe it's because I'm colorblind. Maybe that's why it didn't work for me. But anyway, let's talk about molecules in three-dimensional space. And when we talk about that, what we're actually going to find out is it's also possible to have a molecule that's made up of elements with different levels of electronegativity, and it still be purely covalent overall. So it can have polar covalent bonds, but still be a purely covalent molecule. So how is that possible? Let's talk about that. Let's talk about how many of you have seen Cloudy with a Chance of Meatball?
I have, terrified by it.
Terrified by it.
I hate walking turkeys.
It's one of my favorite. It's one of my favorite cartoons.
It's been a while.
Has anybody not seen it? Okay, I love it because it's got so many nerdy jokes in it. So the reason I'm bringing that up is because if you guys remember in the first one, when he's showing his machine, right, that makes food out of the moisture in the air, and she says, "What's it called?" And he says it's like the Flintstone or something. I can't do it. My kid's like, no. The fur, right? He goes, and then he shows her how to do it. It's like, and it does all of them out. So that's what I think of every time I write this down. The valence shell electron pair repulsion theory. It's the spur theory. That's what I think of. So it says that the shape of a molecule is based on the repulsion between valence electron pairs in the molecule. So, what do we mean by repulsion?
Repulsors.
Repulsors, what does that mean?
Iron Man.
Is that what it was called in Iron
Yeah,
Man?
the repulsors.
Repulsors, really?
Yeah.
Okay.
Yes,
So,
Repulsor technology.
so when you think about that, when he does that, what happens to Iron Man? When he shoots that out,
Energy comes out of him.
and what happened? Which direction does he go? Unless he's like,
He goes back.
he goes backwards, right? So like the first scene where he's trying it out, it's like shoots his arm backwards, right? The first time he does it, or the great scene when he's like, okay, I'm going to start off slow, 10%, and of course if he would have in real life he would have been dead, right? And the movie would have ended right there. He'd have broken his neck and it would have been over. But so repulse is the idea of pushing back, separating from one another, right? If you're repulsed, if a roach runs across in front of my wife, she's repulsed by that, right? She backs up. So repulsion has to do with repelling, right? Separating back. And so we know with positive and negative charges, like charges do what? It's the same charge. They repel, right? That's the idea here with this repulsion theory. So if we have these electron pairs in the molecule, what's going to happen is those electron pairs are going to repel one another. The repulsion theory says that they are separating each other. They're not drawn towards one another. There's repulsion taking place there. And so that's what this has to do with. And in three-dimensional space, let's think about a compound that we're familiar with. So if we think about carbon tetrahydride, which is this, all right, this would be the Lewis structure for that compound, right? You guys agree with that?
I don't think the camera's recording.
Oh, did it stop?
I don't.
I got a phone call. Did it stop when the phone call came through?
I think
It's still going.
Oh, okay.
It's still going. All right. Is that just your way to get your voice on camera? That was just that was.
No, she said it's not. and then she was like, recording.
Is that? Am I here?
Yep.
Cause like,
Am I moving in slow motion?
and then she said it's not recording.
And you looked at it and you're like,
All right, I did wonder because I got a phone call, so I was like, I hope that didn't mess it up. All right, so so this is what that Lewis structure looks like, and this looks great, except this is two-dimensional space, right? We're drawing this on a board. Molecules exist in three-dimensional space, and so this would be if these things are negatively charged pairs of electrons, it would make sense that they would. This repulsion would be taking place and they would be separated from one another. But since it's in three-dimensional space, you'd actually have to look on page 143 to see a 3D drawing of what this molecule actually looks like. And I'm going to try to represent that on my two-dimensional board here, where I've got this kind of bolded line, which is supposed to be coming out of the board, and this dotted line is supposed to be going into the board. So it actually looks something like that in three-dimensional space. And what's happening is these electron pairs are repelling one another. They're trying to get as far away from one another as they can. All right? And since we've got all hydrogens on the outside of this thing here, the maximum distance that they can be separated from one another is 109.5 degrees. All right? We refer to this as the bond angle. It's the angle between the bonds, right? The covalent bonds that are in our molecule. And so what we call this shape is the tetrahedral shape. All right, and like I said, it has a bond angle of 109.5 degrees. Now, I'm going to give you various shapes. We're going to go through several different shapes for these three-dimensional molecules, and that's what I want you to know as we draw these shapes. I want you to be able to tell me what the name of the shape is, and I want you to be able to tell me the bond angle for that shape. Okay? And I'm not asking it here, but you should also be able to tell me if it's an obvious enough. What you're not going to have on the test is you're not going to have that version of the periodic table which shows the electronegativity. But I still might give you an obvious molecule where I say, show me the direction that the electrons are being pulled. So like in the case of this one, all of my electrons are being pulled in this direction. And like I said, I might write a plus on the end here to show that that's the positive side, and which way is the negative side. If I ask you to do something like that, what am I probably going to put as my central angle? Or what atom am I probably going to put in there so you would definitely know that it's more electronegative than anything else?
Fluorine.
I'm probably going to put fluorine, right? Because then it's obvious. It's a no-brainer. It's the most electronegative. It's on the top right.
Please put fluorine.
What's that?
Please put fluorine.
So yeah, I will. I mean, I just expect that, right? Because if I put something in the middle, it's hard to tell without having that other table. But so these are spreading out as far as they can. But here's what you need to realize here: they're actually being pulled inward, but because it's being evenly pulled inward from each direction, then when you have a tetrahedral shape, the overall effect is that they're canceling one another out. All right, think about it like tug of war, right? If I have a guy standing here and I've got somebody pulling on this side, and the same person that's just as strong is pulling on this side, I'm not going to go anywhere, right? I'm not moving one. I know what you're thinking. I'm thinking about if like I'm a Lego figure, my arms just pop off, right? But if I'm not a Lego figure and they're not strong enough, then my arms are going to stay here, and I'm probably going to have trouble with my rotator cuff later, but at least I'm not moving anywhere, right? And so that's kind of what's happening in a tetrahedral shape. Even though there are polar covalent bonds here, because they're being pulled evenly from opposite directions, the net effect is not being pulled in any direction. So it's possible to have a polar covalent bond and yet the molecule as a whole being purely covalent. Does that make sense? Because it's being evenly pulled in the various directions. All right? So anyway, this is the first shape. Now that basic shape here, this shape that we've drawn this in, we call this shape a tetrahedron, right? So a tetrahedron has like a central atom with the four electron pairs around it. All right. So next, I'm going to show you two shapes that are a variation of the tetrahedron. It's like a tetrahedron, but we're going to remove the shared pairs of electrons, and we're going to replace them with a pair of non-shared electrons. So our next shape is the pyramidal shape. And so as our example, I'm going to use ammonia, which is NH3 for this. And so NH3, if we draw the electron dot configuration for NH3, it looks like this. But when we talk about the bond angles, and we talk about the electrons being separated, we actually only consider the shared electron pairs. All right? Those are the ones that are pushing away from one another. And so this shape here, it's like a tetrahedron but with one leg missing. And so it looks like this if we draw it. It's like H over here, and then we got the one coming out of the page here, and then we got the one going into the board here. And the angle of separation for this guy, the bond angle, is 107 degrees. And like I said, this is the pyramidal shape. And then the last thing that we've got is, again, a variation on the tetrahedron, but with one more leg missing. Okay? So an example of that would be water. And so water looks like this. It looks like, so H2O looks like O, H, H. And for this particular one, the 3D version is like this. H is down here with 105 degrees of separation. And we call, let me make sure I put a star next to these, because I want you to know, like I said, I want you to know the shape, the name of the shape, and the degrees of separation, the bond angle, okay? And this is called the bent shape. And maybe since our experiment was bending water, that'll help you remember that, and we were talking about water, it'll help you remember the name of the bent shape. But we've got tetrahedral, pyramidal, and bent. And those are all variations of this basic shape that we call a tetrahedron. Okay? Any questions about those 3D models of a molecule? I have two other shapes I need to show you. I want to make sure that I answer any questions you have. So on a test, I'd say, show me draw a diagram of it, tell me the name of the shape, and give me the bond angle, right? That's what I would be looking for. So I'm going to leave, I meant to leave the pyramidal. Bummer. Let me move it over here. So the pyramidal, because I want you to see the difference. So the pyramidal was like N, where we had H, like this. So we drew that as N with H, H, H. That was pyramidal. And what was the bond angle for that?
107 degrees.
107 degrees, right? A shape that's very similar to that is one that looks like this. This is not a variation of the tetrahedron, and that's basically how you tell the difference. So if you had something like that, and the way this one would be drawn is it would look like and the bond angle would be 120 degrees. What now? Has it stopped recording now? What is it? Something hanging out of my nose? What is it?
My stomach growled as you thought it was.
Man, I was growling up here the whole last class.
Oh my gosh.
All right, so this one's called because it's got 3 legs on it, this is called the trigonal shape. And so how are we going to tell the difference between trigonal? How are we going to know when it's trigonal versus pyramidal? If you were to look at this one versus that one, is there anything that jumps out at you? It's like, okay, yeah.
There's the 2 lines for.
So the 2 lines, it's not necessarily that. The 2 lines are part of it, but the reason the 2 lines are a part of it is because we don't have this pair of non-bonding electrons up here. Okay? So we have like 3 groups of shared electrons with no unshared electrons, right? Here we have 4 groups of electrons. It's just one of the groups happens to be unshared or non-bonding. Okay? So if you look at it and you basically have 4 groups around the central atom, but one of the legs are gone away from the tetrahedron, then you're dealing with the pyramidal. But if you've got something like this where you have 1, 2, 3 groups of electrons around it, then it's going to be the trigonal. And you're right. What you're going to see probably is a double bond there. That's why you only have three groups, right? But it's that you have this central angle and 3 groups around it, and that's what makes it trigonal. And then the last one is kind of similar to our bent shape. But again, the bent shape is like 4 groups of electrons here. It's just 2 are non-bonding pairs. For the bent shape, you've got something like this, like carbon dioxide looks like this. And we've got a bond angle of 180 degrees. And this is called the linear shape. Again, the difference is it's not like the tetrahedron with a couple of legs missing and replaced with non-bonding electrons. We've just got two groups of electrons, shared electrons around the central atom. That's why it's linear. So given all, again, I need you to know the name, I need you to know the bond angle, I need you to know the basic shape. And I'm going to give you a couple of quick rules. It's what I was just talking through, but I'm going to write these down explicitly. Some basic rules for determining the shape. All right, so make sure you know how to use this. Basic rules for determining shape. Man, it is hot in here. We need a ceiling fan. So first step, determine Lewis structure. All right. Second step, if two groups of electrons around a central atom, or if only have two atoms, or only two atoms, then it's linear shape and 180 degrees. All right, that's the first one. Two groups of electrons right here around the central atom, or if we only had two atoms, like when we had Cl, it's linear shape. If, and I'm just going to use the double quote here to show, I mean the same word that's above there. Three groups of electrons around a central atom, then what's the shape name? Anybody know? Three groups of electrons around the central atom.
Trigonal?
Yep, trigonal. And you may be right, maybe it's trigonal. I thought I looked it up and it was trigonal, but that was probably last year when I looked that up. So. All right, so that's the trigonal. Otherwise, there are four groups of E's, of electrons, around the central atom, right? That's our other option. And we've got three shapes that fall in that category. So if no non-bonding E's, then our shape is tetrahedral and 109.5 degrees. If one pair of non-bonding electrons, what's our shape? So it's like a tetrahedron, but with one pair of non-bonding electrons. It's on the board.
Trigonal? Oh no.
There's two that are on the board. One has one pair, one has two pairs of...
Bent?
Huh?
Bent?
The bent has how many pairs of non-bonding electrons? It has a set here, and it has a set here, so it has two pairs. We're talking about the one that has only one pair.
Okay.
So this one right here the pyramidal. So it's the pyramidal, and it's 107 degrees. And then finally, if two pairs of non-bonding electrons, it's bent with 105 degrees. All right, so we have an example on page 147. And it says, what is the shape of HCN? All right. So the first thing, we've got 3 atoms. So we're going to have something that functions as the central atom. How do we figure out which one's our central atom? What was our rule for that? You guys can't see that are watching this online because you're looking this way, but every one of them have fallen asleep on me. Wake up! You guys don't remember? How do you find the central atom?
Oh, the one that needs the most valence electrons.
That's it. The one that needs the most electrons. Hey, you got in there, Jack. Nice.
Finally, took an hour. 15 minutes.
The one that needs the most, and you know what? I want to go ahead and give one to Hannah too, because she let me know that my camera had quit working, even though it hadn't been really. All right. So which one needs the most valence electrons here? Hydrogen only needs 1. Carbon needs 4. Right? It's in 4A. Where's nitrogen?
Isn't 5A?
5A, so it needs 3. So carbon needs the most. So we're going to put carbon in the middle, right? So carbon looks like this. Hydrogen looks like this. And nitrogen's got 5. So it looks like that, right? So what's going to happen is that you're going to have a single bond with the H. And we're going to have a triple bond with the N. And then everybody's got the electrons that they need. Make sense?
What does it?
And we recognize that there's actually a pair of non-bonding electrons on the nitrogen, but that's not going to have any bearing on our shape. What is the shape of this guy? Based on our rules right here. I'm just looking at this, I'm drawing it this way with our covalent bonds.
It's linear.
It's going to be linear, right? Because we've got a central atom with 2 groups of electrons around that central atom. Just these 2 groups right here. So that's going to be linear, and the bond angle is going to be 180 degrees. All right? So that's what I would expect you to be able to do for me on a test or a quiz.
I'm scared now.
You're good. You're good. You got your rules. NCl3, if we were asked to do that, NCl3, we would put the nitrogen needs the most, and so it's going to have Cl, Cl, Cl. It's going to look like that with 1 non-bonding pair on the top. So which one does that correspond here? If we number these 1, 2, 3, 4, 5, which one fits the description of that? How many groups of electrons do we have around the central atom?
3.
1, 2, 3, 4.
Oh.
You have to count the non-bonding pair, right? So we're down here in this section. How many non-bonding pairs do we have? 1. So it's this one right here, pyramidal. With a bond angle of 107 degrees. Does that make sense to everybody? Do you guys see how that works? So you're going to have to put those non-bonding pairs on there to be able to tell the difference between pyramidal and trigonal, right? So that you can see clearly that there's four groups of electrons around it, but one is a non-bonding pair. Okay? All right, so this last thing here, let's see. I've already kind of talked about this, but we'll do an example. And it's the fact that you can have polar covalent bonds, but still have a purely covalent molecule because they're tugging, everything's being tugged on evenly, right? So if we look at SF2, this is an example on page 149, SF2, and they say, is this a polar molecule or a non-polar molecule? So we talked about purely covalent bonds, give you a purely covalent molecule because the overall pull is the same. So think about the purely covalent idea when we talk about a non-polar molecule. It may have polar bonds, but the net effect of the pulling, because there's opposite pulls for every pull, could still not be polar and be non-polar. So what about SF2? Which one's going to be our central atom for that one?
Sulfur.
Sulfur needs how many?
I believe 6.
It has 6, so it needs 2, right? So what's going to happen there is you've got shared electrons on both sides here with the fluorine hanging off. So it looks like this. So it's going to look like that. This isn't the question for this particular one, but we need to know this. They didn't ask us specifically to give them this, but you need to know what the shape is and the bond angle for this guy. What would the shape be for this? I've drawn it so that it looks like what? Linear. But based on our descriptions up here, if it's linear, it's got to have a central atom with 2 groups of electrons. How many groups of electrons are around sulfur?
4.
There's actually 4, right? 1, 2, 3, 4. How many non-bonding electron pairs do we have? 2. So we're actually dealing with the bent shape, right? So if I were to draw this, it actually needs to look like more like this, right? And for this particular one, our bond angle is going to be what for the bent shape? 105, right? 105 degrees. Bent shape. And so because it's bent, because they're not pulling exactly opposite of one another, which one's the more electronegative here? Fluorine, right? Fluorine is the most electronegative, so they're pulling in this direction. And because of the non-bonding pairs, since they're not pulling evenly across, actually the whole thing's pulling downward. Do you guys see that? So it actually is going to be a polar covalent molecule. Because if it had been linear and it had been pulling exact opposite of one another, it would be a non-polar molecule. But this one's polar because they're both pulling down. All right, so now you've got something else I can ask you about a compound. I could give you the compound, say, give me the shape, draw the Lewis structure, give me the name of the shape, give me the bond angle, and tell me, is it polar or non-polar? Okay? You guys see that? So this one's polar. Let's show you one that is non-polar. Let's do SiO2. SiO2 looks like this. We've got Si, which has, it needs, it's in 6, right? Is that right, 6A? No, wait a minute, it's in 4A. It needs 4, sorry. It's in 4, that's what makes it our central angle. And then O is out here, so what's going to happen is you're going to have 2 double covalent bonds like that. How many pairs of electrons? How many groups of electrons around our central atom?
0.
0?
4.
Or 4? It's either 0 or 4, he says. That's a kind of a big gap there. What if I say it's neither? How many groups of electrons do we have? Remember, when we talk about groups, if it's a double bond, we consider that to be one group.
So
Give us one more try. How many do we have?
got 2 shared pairs.
2. So we got 2 covalent bonds here. So that is this category. So now we're dealing with linear, right? This shape is linear. 180 degrees for our bond angle. And so now, because it's linear, and I lost my
Find the
top.
left foot.
Oh, there it is, thank you. Because it's linear, which one's the more electronegative? Si or O?
Oh.
O is? Yeah, because it's on the far right, up top, higher, so it's going to look like this. But notice with this one, they're each pulling opposite of one another. So what's the net effect of this? Is it going to be polar or nonpolar?
Non-polar.
Non-polar, because it's like the guy tugging on, right, each arm here. 2 people that are pulling just as hard as the other. So the net effect is I'm not going to be pulled anywhere. Just my arms will eventually pop off. It's nonpolar, all right? And actually, they don't write it with a dash, so ignore my dash there. I was just kidding about that. Just messing with you guys. Ha! It's funny, Mr. Walker.
So very funny.
So funny. Such a crazy guy, right? All right. How are we doing on time? Oh, man, we got 2 minutes. Just long enough to talk about polarity. Why is polarity important? What are we talking about when polarity? We're talking about the fact that we've got partial charges, right? I love it when the board just decides to do that.
Gives up on you.
So nice. It's like, we're done. I don't care if you got 2 minutes.
No,
We're done.
refilm the video.
What?
Refilm the video.
I know, the whole thing. It's all ruined. Why is polarity important? Polarity determines if a compound can dissolve in another compound. All right, so one of the chapters we're going to spend quite a bit of time on this with mixtures, where we create mixtures, we dissolve some substance in another substance. And the reason that salt dissolves in water, but yet it won't dissolve in oil, is because salt is an ionic compound, and ionic compounds are held together by what? I should have given you guys the answer ahead of time, so it was like they're like, wow, the class is brilliant. What do we have in ionic compounds? They don't share electrons.
It's given the electrons.
They're given the electrons, and so they have charges, and so it's those opposite charges that hold it together, right? An ionic compound actually kind of looks like a lattice of positive and negative atoms, just all connected with one another because of those charges, right? But with covalent compounds, they share the electrons. Well, that means that ionic compounds have charges in them, right? And what did we find out about polar covalent compounds? They have partial charges. And so as it turns out, polar covalent compounds like water will dissolve ionic compounds because they both have charges. It's the fact that they carry charges that makes it possible for them, one to dissolve in the other. But you can't dissolve salt in oil because oil is a purely covalent substance instead of a polar covalent substance. It doesn't have those partial charges like water does. So this is just all I want you to know regarding polarity. Polar covalent compounds can dissolve other polar covalent compounds. And ionic compounds. Because both contain electrical charges. I'll let you write that down, and I'll give you the next. Yes. Oh, sorry. That's
Sorry,
just
no.
how you rest your. I always rest my arm like this.
Like this.
All right, purely covalent compounds. It always cracked me up in Civil Air Patrol that if you're going to ask a question, you do this. You don't do that. You got to do this. Purely covalent compounds can dissolve other. Wait a minute. Purely covalent compounds. Sorry, I jumped definitions there. My bad. Purely covalent compounds or nonpolar. Right. That's another way to write that. Nonpolar compounds usually only dissolve other non-polar compounds. Okay?